Two nuclear reactors sit beneath the flight deck of a Nimitz-class carrier. Each one produces enough thermal energy to power a mid-sized American city. Roughly 550 megawatts of heat, translated into propulsion, electricity, steam. The ship carries enough enriched uranium to steam for 13 years without refueling. There is, by almost any measure, no vessel on Earth with more raw energy density than a nuclear supercarrier at sea. And yet, on a June afternoon in the Persian Gulf, when the sea surface temperature climbs past 32 degrees Celsius and one of the ship's distilling units trips offline, the flight operations officer gets a phone call that has nothing to do with the reactors. It has to do with water. Here is the paradox. The most powerful warship ever built. A hull that costs $8.5 billion, that carries 80 aircraft, that projects American air power across 1,000 miles of contested ocean, can have its sortie rate throttled by a worn gasket in a piece of equipment that costs less than a new pickup truck. The reactors are fine. The catapults are ready. The F/A-18 Super Hornets and F-35C Lightning IIs are fueled and armed on the hangar deck. But without enough fresh water, none of that matters, because the catapults need steam, the crew needs to drink, and the reactor coolant loops need makeup water that cannot come from the sea. This is not a story about failure. It is a story about a constraint so fundamental it is built into the architecture of every carrier the United States Navy has ever operated, and about why that constraint becomes most dangerous in exactly the waters where the Navy most needs to project power. Stay with this. By the end, you will understand why the most energy-rich warship in the world is rationed by plumbing, and what that means for the carrier strike groups the Pentagon is counting on across the Western Pacific and the Gulf right now. The Nimitz-class entered service in 1975. USS Nimitz herself is still in commission. 10 ships in the class, each displacing roughly 104,000 tons at full load, each powered by two Westinghouse A4W pressurized water reactors. The Ford class follows the same logic with two A1B reactors and more electrical output, but the water problem is structurally identical. In some ways worse, because the electromagnetic aircraft launch system draws more power from the ship's electrical bus and generates more waste heat in components that also need cooling. For 50 years, the United States Navy has organized its power projection strategy around these hulls. A carrier strike group built around a Nimitz or Ford-class ship typically includes one or two Arleigh-Burke-class destroyers on the screen, a Ticonderoga-class cruiser for air defense coordination, a Los Angeles or Virginia-class submarine running submerged on the flanks, and a supply ship that keeps the whole formation fed. The carrier is the centerpiece, the reason the formation exists, and the node through which all strike and air defense sorties flow. The strike group's reach is measured in aircraft sorties per day. In a sustained surge, a Nimitz-class air wing can generate roughly 120 to 140 sorties in a 24-hour period. That number is what a combatant commander plans around when he is asked how much air he can put over a target. And that number depends, more directly than most people realize, on how much fresh water the ship can make. What's most surprising about this constraint isn't that it exists. It's how far upstream it reaches into every system on the ship. The distilling plants aboard a Nimitz-class carrier are multi-stage flash evaporators, MSF units in Navy shorthand. The ship runs several of them in parallel. The principle is straightforward. Seawater enters a series of chambers held at decreasing pressures. As pressure drops, the water flashes to steam at temperatures below normal boiling point. That steam condenses on cool surfaces and is collected as distillate. A second technology, reverse osmosis, has been added to newer configurations and to the Ford class as a supplement. High-pressure pumps force seawater through semi-permeable membranes that block salt ions and pass fresh water molecules. The RO units are more energy efficient at moderate temperatures. The MSF plants handle higher throughput but are thermally sensitive. Together, on a fully operational ship in temperate waters, these systems produce roughly 400,000 gallons of fresh water per day. That sounds like an enormous number until you start allocating it. A crew of approximately 5,000, the carrier and its air wing together, consumes somewhere between 30 and 50 gallons per person per day for drinking, cooking, showers, laundry, and medical use. Call it 35 gallons as a working number. That is 175,000 gallons per day just for the crew. Add the food service operations, the medical bay, the berthing block washdowns. You are already at roughly 200,000 gallons before you touch any mechanical system. Then come the catapults. The C-13 steam catapult, the system that has launched every fixed-wing aircraft from American carriers for decades, works by storing high-pressure steam in an accumulator and releasing it down a track in under 3 seconds, accelerating a 45,000-pound aircraft from 0 to 150 knots before it reaches the bow. Each launch consumes a measurable slug of steam. In a high-tempo flight day, with aircraft cycling on all 4 catapults, steam consumption from catapult operations alone accounts for somewhere between 80,000 and 120,000 gallons of fresh water equivalent per day. Water that becomes steam, that drives the catapult, that must be replaced from the ship's distilling capacity. The Ford class replaces the C-13 with the Electromagnetic Aircraft Launch System, EALs, which uses linear induction motors instead of steam. In principle, this should reduce the freshwater demand tied to launches. In practice, the EAL system introduces its own thermal management requirements in the energy storage capacitors and drive electronics, and the ship still needs substantial fresh water for the reactor coolant makeup and for the crew. The hydraulic catapult water problem goes away. A different set of cooling water demands takes its place. This is the first layer of the paradox. The ship produces 400,000 gallons a day, but the margin between production and demand, at full operational tempo, in hot weather, with all systems running, is smaller than the capacity of a single distilling unit. When one unit goes offline, that margin disappears. Here is the complication that most analyses skip past. The Persian Gulf is not the North Atlantic. Gulf water in summer runs between 32 and 35 degrees Celsius at the surface, sometimes higher in shallow inshore areas. That thermal input degrades the efficiency of both distilling technologies in ways that compound each other. For multi-stage flash evaporators, higher feed water temperature means a reduced temperature differential between the incoming seawater and the flash chambers. The thermodynamic efficiency of the process depends on that differential. When it shrinks, the plant produces less distillate per unit of heat input. Output can fall by 15 to 20% from rated capacity before any mechanical fault occurs, purely from the ambient seawater temperature being higher than the design baseline. For reverse osmosis membranes, the problem is different but equally punishing. Gulf water salinity runs approximately 40 to 43 parts per thousand, meaningfully higher than open ocean salinity of around 35 parts per thousand, because the Gulf is semi-enclosed and evaporation losses are high. Higher salinity means higher osmotic pressure that the RO pumps must overcome. The pumps draw more power, the membranes foul faster, and membrane replacement cycles shorten. A membrane stack that lasts 12 to 18 months in Pacific operations might need replacement in 8 to 10 months of Gulf deployment. Gulf water also carries higher concentrations of biological fouling agents, microorganisms and particulates that clog the intake filters and the membrane surfaces faster than cooler, cleaner open ocean water. The result: the ship's distilling capacity in the Persian Gulf, the theater where it has operated most continuously since 1990, is structurally lower than the nameplate capacity the system was designed to deliver. The environment where the carrier is most politically and strategically deployed is the same environment where its water-making capability is most degraded. One detail that sticks when you go through the maintenance records and the operational studies: the Navy has known about this thermal degradation problem for decades. The Nimitz-class was designed in the late 1960s and early 1970s. The Gulf deployment tempo that emerged from Desert Storm, through the 2000s, through the current era of persistent presence, was not the design case. The ship was engineered for cold water operations, and it has spent much of its operational life in warm water theaters. When a distilling unit does trip offline in the Gulf, the sequence that follows is worth understanding in some detail. An alarm sounds in the engineering spaces, a low-level tone that the watch team has been trained to recognize above the ambient noise of the ship's machinery. The engineering officer of the watch dispatches a petty officer to the unit within minutes. A visual inspection confirms the fault. In a typical case, a flash chamber seal has degraded under thermal cycling, or an intake filter has fouled beyond its service interval. The petty officer radios the report up the chain. Within the hour, the engineering department's water king, the senior enlisted specialist responsible for the distilling plants, has assessed whether the repair is within the ship's organic capability or whether it requires parts not currently in the magazines. That assessment drives everything that follows. The economic layer of this problem is where the paradox gets genuinely sharp. A Nimitz-class carrier costs approximately $8.5 billion to build and roughly $700 million per year to operate, including the air wing. A Gerald R. Ford-class ship. USS Gerald R. Ford, USS John F. Kennedy, USS Enterprise, comes in closer to $13 billion in acquisition cost, plus the cost overruns and the years of post-delivery work to bring the new systems to reliability. The carrier strike group as a whole, including the Arleigh-Burke destroyers, the Virginia-class submarine, the supply ship, and the Air Wing aircraft, represents somewhere between $25 and $35 billion in capital assets, plus the annual operating budget. Against that number, consider what actually gates the sortie rate when the water system degrades. An MSF evaporator gasket, the elastomeric seals on the flash chambers, costs a few $100s per unit. A full seal replacement kit for one evaporator unit runs roughly $2,000 to $5,000 in parts, plus the labor of the ship's engineers to disassemble and reassemble the unit underway. An RO membrane stack, the consumable heart of a reverse osmosis unit, costs approximately $40,000 to $60,000 per stack, depending on the specification. The high-pressure feed pumps that drive the RO system, when they need overhaul, run in the range of $150,000 to $300,000 for parts and depot work. Here's the take that will probably draw some pushback. The cost asymmetry here is not a design flaw the Navy failed to address. It is a deliberate engineering trade-off that simply looks irrational from the outside. The ship cannot carry an unlimited number of spare evaporators. The weight and volume budget of a carrier is allocated down to the last cubic foot. Every spare part carried displaces aviation fuel or ordnance or food. The decision to run a relatively thin margin on water production capacity is a consequence of trying to maximize the offensive payload the ship carries, and accepting that underway replenishment and port calls will resupply the consumables that cannot be stockpiled aboard. The problem is that the Gulf deployment tempo reduced the frequency and reliability of those resupply opportunities. A carrier running a sustained combat air patrol cycle, with strict emissions control and a threat picture that makes port calls impractical, is operating exactly the scenario where the thin margin on water production becomes a real constraint. Now, pull back to the strategic level, because this constraint does not exist in isolation. It exists inside a larger conversation about how the United States Navy sustains carrier power projection against a peer competitor with the ability to track and target carrier strike groups at range. The People's Liberation Army Navy now operates 3 aircraft carriers. The Liaoning, a refurbished Kuznetsov-class hull, serves primarily as a training and development platform. The Shandong is an indigenous development of the same ski jump design, and the Fujian. The Type 003 is a genuinely new capability, a conventionally powered but catapult-equipped carrier with what appears to be an electromagnetic launch system similar in concept to the Ford's EALs. Beijing's shipbuilders completed the Fujian faster than most Western analysts projected. But the strategic threat to American carrier operations in the Western Pacific comes less from the plans carriers than from the weapons designed to target American carriers. The DF-21D, the so-called carrier killer, is a medium-range ballistic missile with a maneuvering re-entry vehicle designed to strike moving ships at sea, with a reported range of roughly 1,500 kilometers. The DF-26, longer-ranged at approximately 4,000 kilometers, and capable of carrying either conventional or nuclear warheads, extends that threat umbrella across the entire Western Pacific and into the Indian Ocean. The response to this threat has been to push carrier strike groups further from the Chinese coast, operating from ranges where the DF-21D cannot reach, and where the DF-26 must be vectored by a surveillance and targeting chain that takes time to function. That push outward extends the carrier's lines of communication and its dependence on underway replenishment. It also means the carrier is operating in open ocean environments where the threat picture may look different, but the water-making challenge does not go away. Here's the part that does not make sense on the surface. The solution to an anti-ship missile threat that requires operating further from land is also a solution that makes the logistical tail longer and the water resupply cycle more extended. The carrier needs to sustain itself for longer periods without a port call or a replenishment ship alongside. That requirement, driven by the missile threat in the Pacific, runs directly into the water margin problem that the Gulf deployments have been exposing for 30 years. So here is where we return to the central question. When an evaporator drops offline mid-deployment, not a catastrophic failure, just a worn seal, a fouled membrane, a pump bearing that needs replacement, the commanding officer faces a real-time resource allocation problem with no clean answer. Option 1. Ration the crew. cut shower frequency, reduce laundry cycles, tighten the galley's water budget. This buys back somewhere between 30,000 and 50,000 gallons per day, depending on how aggressively it is enforced. It preserves catapult steam capacity. The flight schedule runs at full tempo, but crew rest and morale begin to degrade. A carrier deployment runs 6 to 9 months. Fatigue on the flight deck is not a soft concern. It is a direct factor in the accident rate for a job that already produces more peacetime fatalities per capita than almost any other in the military. Option 2. Throttle the flight schedule. Reduce sortie generation by 15 to 20%. This cuts catapult steam demand, which cuts water demand, which keeps the crew at a sustainable quality of life. But it also cuts the sortie rate that the combatant commander is planning around. In a real contingency, that 15 to 20% reduction in sorties is not an abstraction. It is a real reduction in how much ordnance reaches a target set in a given 24-hour window. Option 3, the one the maintenance crews are trying to execute the whole time, is to get the offline unit back. But on a ship underway in the Persian Gulf, with limited spare parts and engineers who are also managing 50 other maintenance priorities, that timeline is not always inside the commanding officer's control. The Navy's shipboard maintenance doctrine allows for emergency resupply of critical spare parts by carrier onboard delivery. A C-2A Greyhound or the newer CMV-22B Osprey can fly a replacement membrane stack or a seal kit out to the ship within hours if the part is on the beach. But that requires the logistics chain to have the part in theater, which requires someone to have predicted the failure in advance. Put yourself in the commanding officer's seat for a moment. You have been told that your strike group is the forward deterrent presence in a theater where the Joint Force Commander has been briefed that a crisis may develop within the next 72 hours. Your water production is at 80% of rated capacity. Your maintenance officer tells you the offline evaporator will be back up in 18 to 36 hours. Do you cut the flight schedule now, preserve crew condition, and risk being caught at reduced tempo if the crisis moves faster than the maintenance schedule? Or do you run full operations, knowing you are burning through the water reserve and will have to ration the crew if the repair takes longer than projected? That question does not have a textbook answer. It is a command judgment call, made under uncertainty, with real consequences in either direction. The officers who have faced it describe a particular kind of pressure. Not the dramatic tension of a combat decision, but the grinding arithmetic of a resource problem, where every hour of delay narrows the available options, and where the crew watching the flight schedule knows, even without being briefed on the details, that something has changed. The reserve margin itself deserves a closer look, because it is the number that makes the decision more or less forgiving. A Nimitz-class carrier holds fresh water in tanks distributed across multiple compartments for damage control redundancy. Total tankage capacity is in the range of 400,000 to 500,000 gallons. At full operational tempo, full crew demand plus catapult steam plus makeup water for the reactor coolant loops, the ship consumes its production output almost as fast as it makes it. The reserve represents somewhere between 12 and 24 hours of full tempo operations without any production. At reduced tempo, no flight ops, crew rationing, that same reserve stretches to 3 or 4 days. 12 to 24 hours of margin at full combat tempo on an $8.5 billion hull. This is why economists who study force readiness talk about input constraints in complex systems. The point in the production chain where a cheap, ordinary component gates the output of an extraordinarily expensive platform. The classic example from manufacturing is the theory of constraints. A factory's output is limited not by its most capable machine, but by its most constrained one. The carrier is the most capable machine in the American military's arsenal. The distilling plant is the constraint. What's striking about this particular constraint is that it is not invisible. The Navy has known about it, studied it, and worked around it for decades. The operational logs of every Nimitz-class carrier that has deployed to the Gulf contain entries about water plant maintenance, about sortie rate adjustments tied to distilling capacity, about emergency parts deliveries. The institutional knowledge is there. What is harder to solve is the fundamental thermodynamics. You cannot redesign the Persian Gulf. The question for the Ford class, and for the future CNO, and for the Pentagon as it tries to manage both a Pacific and a Gulf presence simultaneously, is whether the electromagnetic systems on the newer ships actually reduce this vulnerability or redistribute it. Early operational data on USS Gerald R. Ford suggests that the EAL system, once its reliability issues were addressed after years of post-delivery work, does reduce the steam demand tied to launches. But the crew demand does not change. The reactor cooling demand does not change. And the Gulf environment remains what it is. There is a broader strategic dimension the water constraint illuminates, and it goes beyond the mechanics of distilling plants. The United States Navy has maintained a continuous carrier presence in the Persian Gulf through Fifth Fleet, headquartered in Bahrain, almost without interruption since Desert Storm. That presence has consumed carrier operating hours, air wing flight hours, and crew deployment time at a rate that has shaped the readiness of the force. The ships that have cycled through the Gulf have returned with higher maintenance backlogs, more worn aircraft, and crews with higher rates of operational stress injuries than ships that spent comparable time in the Pacific or Atlantic. At the same time, the Western Pacific has become the primary theater of strategic concern. The Indo-Pacific Command, with its focus on the South China Sea, the Taiwan Strait, and the first and second island chains, has been asking for more carrier presence. More time on station, more strike group deployments, more exercises with allies including Japan, South Korea, Australia, and the Philippines. The Navy's carrier force consists of 11 ships, 10 Nimitz-class hulls, and USS Gerald R. Ford. At any given time, roughly 3 to 4 are in active deployment or workup cycles. The rest are in maintenance, overhaul, or training, sustaining simultaneous presence in 2 geographically separated theaters, the Gulf and the Western Pacific. While keeping the maintenance cycle from collapsing is a problem that has come up in every major fleet readiness assessment since 2010. The water constraint is one face of a larger readiness equation. Every Nimitz-class ship that runs a Gulf deployment under thermal stress comes home with a distilling plant that needs more work than a ship that ran a comparable deployment in cooler waters. That maintenance work takes time, which takes the ship off the deployment schedule, which reduces the number of hulls available for the Pacific presence that combatant commanders are requesting. Here's what most people assume, that the limiting factor on American carrier power projection is munitions. How many Tomahawks and JDAM, EERS, and AIM-120S the ship and its strike group can carry? It isn't. The limiting factor, at the level of sustained operational tempo over a multi-month deployment, is the intersection of crew, endurance, maintenance cycles, and water production capacity. Those 3 things are linked more tightly than any of them are linked to weapons loadout. The Fujian's Type 003 hull uses conventional propulsion, steam turbines fed by oil-fired boilers, not nuclear reactors. That choice made the ship cheaper and faster to build. Beijing shipbuilders in Jiangzhou completed her in a timeline that surprised Western observers. But it also means the Fujian carries fuel oil in tanks that limit her range and her time on station between replenishments. A conventionally powered carrier in the South China Sea can count on proximity to Chinese ports and the plan's growing underway replenishment fleet. A Nimitz-class carrier operating at the ranges dictated by the DF-21D threat umbrella cannot. There is a genuine asymmetry that runs in both directions. The American carrier has the endurance of a nuclear plant and a self-sustaining water system, but that system is thermally vulnerable. The Chinese carrier has shorter legs and greater dependence on shore-based logistics, but it does not operate in the Gulf. Each design reflects its operator's geography and strategy. What does it mean, then, that the most powerful mobile weapons platform ever built measures its combat endurance? At the margin. In water? It means that the infrastructure of the mundane and the infrastructure of the strategic are the same infrastructure. The pipe that takes warm Gulf seawater into an MSF evaporator and the catapult track that sends an F-35C into the air are part of the same system. You cannot optimize one without understanding the other. So here's the question worth sitting with. If you are a naval planner in the Pentagon right now, managing an 11-carrier fleet across 2 theaters, watching Beijing commission new hulls and new missiles on a schedule that has repeatedly outpaced Western estimates, do you invest the next dollar in a more survivable anti-ship missile defense for the Arleigh Burke destroyers on the carrier screen, or in solving the water production vulnerability on the carrier herself? One makes the ship harder to hit. The other makes it harder to stop. They are not the same problem, and the budget does not stretch to both at once. The catapults are ready. The F/A-18 Super Hornets and F-35Cs are spotted on the flight deck. The reactors are running at steady state, producing more raw energy than most nations can generate from a single power plant. And somewhere below the waterline, A multi-stage flash evaporator is processing warm, salty Gulf water into the fresh water that holds the whole operation together, one gasket at a time. We'd genuinely like to know, in your read, is this a logistics problem that engineering can eventually solve? Or is it a fundamental feature of projecting power at distance? The kind of constraint that no amount of technology ever fully eliminates? Drop your answer in the comments. And if you want to follow the thread from the carrier to the ships that protect it, how the Arleigh-Burke's Aegis system is being stretched to cover threats it was never designed to face, that one is coming next.